Hi. So my name's Kevin, and I am the lead engineer on the Amazon SageMaker notebook team. Um, some of you might already know we launched last November during AWS reInvent, and we do a lot of Jupyter. So Jupyter is a really important part of the SageMaker product. In this morning's keynote, we talked a little bit about many of the components of Amazon SageMaker. And today, I just wanted to give you a little bit of a sneak peek and just an inside look into some of the things we've been doing on the engineering side that you might find interesting with something called kernel containerization or notebook containerization. So by the end of this talk, I hope you can walk away with a better understanding of the following four things. First, I'd like you to understand my definition of what a containerized notebook is, or a containerized kernel. The second thing is I'd like to give you a little story of two use cases we had internally. Perhaps you can apply these to your daily work. Third thing is I'd like to give you just an overview of how we built these implementations, give you a couple of technical deep dives into what we did while implementing these things, some of the challenges we came across, how we solved them. And lastly, I'll give you some tips on implementing your own. So in this talk, I'll try not to be too technical, but I do assume that you have a basic understanding of how a kernel works, how a Docker container works. And don't worry, none of this will be on the test later, and all of the slides will be available for download from the JupyterCon website at the end of this talk. Okay, so before we dive into the nuts and bolts, the first thing I'd like to do is just give you a very quick overview of the relevant moving pieces. So the first thing I'd like to talk about is Amazon SageMaker. So this is the service I work on, and SageMaker is a fully managed service that makes it easy to build, train, and deploy machine learning models in the cloud. The build portion of this diagram is the part that I work on. That's the Jupyter notebooks. So for completeness, and this will be a little relevant later, SageMaker also includes a few other things: a scalable model training and tuning service, a model hosting service for both real-time and batch predictions, and a broad selection of ready-to-use algorithms. The second service that I'm going to be mentioning is AWS IoT Analytics. This is a totally different AWS service, which is a fully managed service that makes it easy to run sophisticated analytics on massive volumes of IoT-related data. Some things you can do with analytics are also integrated with SageMaker. For example, it can automatically create notebook files for you, which are pre-configured to look at all your IoT data. From there, you can do advanced analytics, train machine learning models, and so forth. And in fact, today, as a coincidence, we're also launching a new feature in IoT analytics, which lets you run notebooks on a schedule or based on a triggered event. That's being announced today. I'm not a trained keynote speaker, but that's happening in Anaheim, California, more or less as we speak. So a lot of people love containers. Who here loves containers? Wow, that's a lot of hands. Great. Okay. You can put a lot of things in a container, obviously, and containerizing is just putting things in a container. So here, what are some examples? Well, first, the whole operating system goes in the container. That's the first line of your Docker file, Amazon Linux, Ubuntu, CentOS, etc. And from there, you put in your applications. You could put in the Jupyter Notebook server. You could put in NB-convert. You could put whatever application you'd like in there. You could throw notebook files in a container. Some people might do that. Some people might not. And you might even put all of your other stuff, your dependencies, your libraries, your SDKs. If you're using Conda, throw the Conda environments in there. So a lot of things can go in the container. And then there was one thing that we kind of thought about and said, what if we put something else in there? What if we put a running kernel in the container? So not the whole Jupyter server, just the kernel. And what could we do if we did that? So I'm going to tell you a story about two Davids at Amazon I happen to know, and what they did with this idea. So the first David was an engineer working on the SageMaker team. This was late last year, right before the reInvent launch, working on something called LDA. LDA is a topic modeling algorithm. I can't pronounce the whole name, so I'll save you from that. Thank you. The Dirichlet was the part I was a little afraid of. So David's implementation, and is this the right picture as well? I hope I got the right one. So David's implementation was half written in Python, half written in C++, and he's trying to put together a container. And this container is intended to run on the SageMaker platform, data in, model out. So he's writing his unit tests like any good engineer. He's writing small test cases in his Jupyter notebooks, making sure the algorithm works appropriately. And he's iterating really fast, getting the performance numbers better and better and better every iteration. And he's doing these smoke tests. And in a smoke test, he's using the New York Times data set. So if you've never used this data set, it contains about 1.8 million New York Times articles over the past 30 years or so. And it contains summaries, hand-verified tags. And this is a great verification data set to use for this algorithm to make sure it was working appropriately. So he runs these smoke tests. They take about 10 minutes to run. And while the smoke test is running, well, his laptop, his desktop, totally hosed. This is using every core, every last bit of the machine. And so this was good time for tea. He's Irish, he loves tea, so he would use these 10 minutes appropriately. And in case you're wondering, he's not using a very weak machine. He's using a cloud desktop, which has about 36 cores, 60 gigabytes of RAM. This is a serious beast, and it still takes 10 minutes to run. So he's getting towards closer to the launch, and he says, I still want to do more than just this New York Times data set. I want to do the Wikipedia data set. Now, the Wikipedia data set, if you've never used it, is about 10 gigabytes compressed of a bunch of Wikipedia articles annotated in a similar way. Now, to run this data set, unlike New York Times, takes about 6 hours. So he does like tea, but he doesn't like that much tea. And you can't really iterate if every time you iterate, you have to wait 6 hours. So he starts thinking, well, my end result is going to be a container. It's going to run on SageMaker. What if I run my smoke tests on SageMaker, which at the time was pretty close to launch, more or less usable. So he's like, but how do I do that? I still want to use my Jupyter notebook. I still want to iterate quickly. And I want to do a majority of my development locally. I just need to run the big heavy lifting stuff up in the cloud. So he kind of set out, hacker extraordinaire, to solve this problem. So let me dive into what David was trying to do. So he's developing this algorithm in something very similar to a SageMaker notebook instance. It uses Anaconda environments for dependency management. It's running with a bunch of local storage attached for local data and all of his notebooks, as well as the algorithms code, the C++ and the Python. So that's what he was starting with. And he's trying to get his code over onto the right-hand side, container world, the training service, the hosting service. So at this time, back in November, on the notebook side, there were no containers anywhere. It was really just a raw box, root accessed, hack away, and there's just nothing container related. So he's trying to build one of the three types of algorithms. There are actually three types of algorithms and containers that we support in SageMaker. He's trying to work on the center one. Customers can also, of course, build their own, and we provide several others that are out of the box, designed to work with popular frameworks like TensorFlow or MXNet. And in case you're wondering, a lot of this data actually all the data is stored in S3, so the New York Times data set, the Wikipedia data set, your training data, and so forth. All right, so this is the loop that he's being stuck in, the 6-hour loop. So he could, of course, from his just basic build tools, write a little script that does all of the things, package up his code, run the compile step, run the build, and then upload it to Amazon ECR. Amazon ECR, in case you're not familiar with it, is a Docker repository for storing Docker images. and then calling the SageMaker code, the APIs to actually run the training. And this could have been a really simple bash script, but he wanted to iterate faster. He wanted to compare the results run over run to see if the performance was getting better, the accuracy was getting higher. And where else do you do that? You do it in a Jupyter notebook. So he said, I'm going to do everything inside of Jupyter. So the first thing he did to reach toward this goal is he built a kernel spec. And it's a kernel spec, if you've never defined one before, it's really just saying what process to run. And generally speaking, out of the box, it's the IPython process. He just added Docker to the front of it. So now the kernel's running inside of a container. Next thing he did is he built a bunch of convenience functions as magics, Jupyter magics. For example, let's say when a training run was complete, it would pull down all of the data back as data frames or other Python objects so he could visualize them, compare them run over run. He probably built about 20 different magics, some higher quality than others, but this was hacking time. This was the rush to ship, so that's what you get. And it did a bunch of things. I've mentioned many of these, and it would also perform the packaging that I mentioned. So when I say packaging, it would actually take that kernel, the runtime state of it, the environment variables, the dependencies, the notebook file itself, squash it in the container, shift enter, there it goes, it's running on SageMaker. Really, really great workflow. And the last thing he did, just for fun, is he built a bunch of widgets. And these widgets let you view the job progress as interactive progress bars. Really, really great stuff there. Ton of ideas. And believe it or not, he actually worked on the LDA algorithm implementation during this time too. So I'm going to give you a quick deep dive of just a couple little snippets of code just so you can understand the complexity of what he built. This is the kernel spec. That's the whole thing, by the way. I just remove a couple of connection details. It's very, very small. It's a little bit of JSON. And this just defines what happened. And you'll notice earlier I said it runs Docker, but actually he wrote a little wrapper script called David's Kernel Launcher, and that actually launched Docker. The reason he did this was to get a little bit more dynamic control over what parameters were being passed. Now, if you're a Docker head, you might appreciate this part. This is an example of the Docker command line, which was generated by the kernel launcher. So once again, you can see that really all he's doing is he's mounting a bunch of things inside of the container, running the IPython process, and mapping a few ports. Jupyter does use TCP to message in between the Jupyter server and the kernels, so there was a little bit of network trickery that went on to make that work. And once again, he uses a small wrapper script inside of the container as well, just to provide a little bit more context and make things less hard-coded. So a few other little tiny things that David did while he was working on this implementation. The first thing he did is he experimented with this concept of a parameterized notebook. So a parameterized notebook is a notebook that accepts parameters at runtime. And he was thinking maybe in some future iteration, an entire notebook could be dispatched as a training job, maybe be reusable, maybe be used for hyperparameter optimization. And he found a really nice library called Papermill, which I think some of the contributors are floating around here at JupyterCon this week, so say hi to them. Are there any contributors in the room here to Papermill? Okay, well, thank you anyway. It was a really, really great library. And the second thing he did is he added a flag to his magics to bypass this upload step. And what that meant is that sometimes during an iteration, the actual expensive part was building the container and uploading it to Amazon ECR, so he added a little flag to say, just run the container locally for now. That's all I really want to do. Well, it turns out that he demoed this internally. We have meetups regularly, like a lot of companies do, and he showed off his hackery. And it turns out that his little local mode flag ended up becoming a feature of SageMaker later on called SageMaker Local Mode, which lets you run the SageMaker algorithms locally on a Jupyter notebook so that you can iterate more quickly. Save the compute power as well if you're using a very tiny amount of training data. Second thing he did is, or that happened at that meetup, was a couple of guys from the IoT team showed up just out of interest. They're building this notebook feature. one or two of them are in the room right now. I think Oleg's back there. Wave, say hello. Hi, that's Oleg. He was in the room along with David, the second David, who said, that's a really interesting concept. Very interesting. And of course, I was in the room too, and I kind of made the connections for them. So I view myself as a little bit of a matchmaker. So let's talk about David number 2, and Oleg and Xiang, who worked on this. So David number 2 was a brand new Amazonian software engineer. He's ready to dig his teeth into his first customer-facing feature. And he wants to really impress the team and build something very high quality, production ready, something that we can launch, which we're doing today. And David was trying to solve a different problem. And the problem he was trying to solve was that customers who wrote these IoT analytics notebooks wanted to run them when they were not sitting in front of the notebook server, and maybe when the notebook server wasn't even running. Containers seem like a really good solution to that problem. So there was a customer who approached the IoT team, runs a wind farm. Yep, we have customers that run wind farms. And they said, whenever the weather changes, we want to run the notebook. So if the notebook server is not running, well, that's not going to work. If the dependencies get out of whack, that's not going to work. So let's run them in a container in a serverless environment in a very, very reproducible way. So you could probably come up with a little bit of a homegrown solution. You could tie things together like a cron job, or if you're an AWS power user, you could use CloudWatch events. You could use Lambda functions. You could kind of glue a bunch of things together to run things on a schedule, but they wanted this to be one click. So they said, let's do this containerization thing. Let's just make it really easy. The notebook becomes the container. The kernel that was used goes into the container. We can run it in a serverless environment. That's what we're going to build. So they dive in, and they realize that David number 1 solution was a little bit more, let's say, happy case than sad case. So it didn't always work all the time. For example, if you're trying to install dependencies at runtime, what if the internet isn't available? Or what if the internet is just having a bad day? What if someone hacked into the repository like PyPy or NPM and breaks the dependency chain along the way? I think that's happened recently. So let's just get everything right. Let's just make sure everything is locked in exactly the way it should be run, so that whenever that weather changes, all that windmill data gets fed into some machine learning model for review. So I talked about running on a schedule a little bit, and the other big issue, of course, is that if you just tell your customers, hey, just write a Docker file. Data scientists who've been hacking away at something for a couple of weeks or a couple of months aren't going to retrofit their work always to get the dependencies perfect. So once again, looking at that one-click solution. I talked about it not always working outside your environment as well. So the first thing they did is start from that experience, that one click. And this was the first drawing of what they wanted to build. Very, very simple. They used a very sophisticated desktop paint application that I won't name to build this prototype. And it's really simple. Just an extra toolbar button, toolbar item, a modal dialog, click the button and go. No idea how to build it. Start with the dialog. So they send it off for review. We have a team meeting. And we say, OK, let's move the button to the toolbar, make it more visible. And let's also build it into a multi-step wizard-like interface to do things like specifying the metadata, getting the notebook variables, determining where the container is going to go, like which repository, and then provide some real-time progress on the containerization operation. So let me give you a quick demo of what this looks like. This is about a minute and a half long, and it'll actually show the feature in action. So this is a brand new Jupyter notebook, and you can see there's a whole new list of kernels. In addition to the regular kernels like the Python 2 and the Python 3 kernel, there are these special containerized kernels. So choosing one of those to create the notebook file, throw in your Python code. You can see that it runs just fine. And now let's get this notebook running on a schedule in a container. Click that button, give it a name, And you'll notice it's also identified all the variables in the notebook so that if at runtime we want to provide them dynamically, we can. Then it looks to see all the repositories that are accessible to you from that context, or create a new one. You can see in this case, we're creating a new repository called JupyterCon. And from there, make sure everything looks good. And then we containerize. And that's really about it. And now that container can be run on a schedule in more or less any environment that can accept a Docker file. The AWS IoT feature has a beautiful console where you can define the schedules, the triggers, and so forth. So I won't speak too heavily to that experience, but this is really a vanilla Docker file. It can be run anywhere. You could create a Lambda function that runs it once a week. You could download the Docker file and run it somewhere else. You could invoke it within a Jupyter notebook if you really wanted to. It's just a plain old Docker file. Nothing especially proprietary about it. So yeah, that's the feature. And that is available today as well. So now that you see it in production, let me talk a little bit about all the parts that were involved in building it. So on the client side, everything is managed in a single module called IOTA Notebook Containers. And this really does all of the work. It installs all the functionality into the Jupyter Notebook, brings that toolbar button alive, gets the containerized kernels available in that drop-down box. So the first thing is just a very simple shell script. IoT runs the script for you. You could run it yourself if you'd like. And that gets the kernels in that list. And this just runs a script that creates all those kernel specs like I showed you before. It's a little bit more refined than David #1's version, but it essentially does the same thing. And this is all done within some Python code. So like many Jupyter extensions, this extension is split between two halves, the notebook extension and the server extension. And the server extension is the part that runs alongside the Jupyter process. It's Python. The notebook extension runs all in the browser. It's JavaScript. So that server extension has basically two jobs. First thing it does is it manages all of the interactions with Amazon ECR. It deals with the credentials. It deals with discovering the ones that are accessible to you based on your role, and also manages creating new ones on the fly. And the other half is the real interesting part, which is the thing that creates the kernel images. And this has a bunch of logic in it to take whatever Jupyter environment you're in and captures it as perfectly as possible so that it can be run later accurately. And for the Docker heads in the room, the containers that are produced use a very standard open container spec annotation to store all those variables. There's no hidden metadata store somewhere that keeps track of these variables. Everything is right in the Docker file, right in the metadata. There are no tricks whatsoever involved. So who'd like to do a couple of deep dives on a couple of these components? And like I said, none of this will be on the test. And most of the source code will also be available at the end of this talk too. Okay, so the first thing is that kernel container creator. This is the thing that's run at install time, the first time you use this thing. And I just gave you a little tiny snippet of the code, and this is the part that creates the Docker files. So each one of those containers has a Docker file associated with it. And if you've never worked with Docker from within Python, there's actually a beautiful Docker library that makes it really easy to create Docker files and interact with Docker without having to shell out to a bunch of CLI commands. So you can see here, we create the header of the Docker file as a string, and then we create a dictionary that identifies all the mounted volumes. You run build, and then it puts together all the commands for you under the covers. Just a really interesting thing I figured you might be interested in if you're interacting with Docker a lot in a programmatic way. It's a really great library. So this is a different snippet of code. This is the thing that installs all of the kernels. And once again, this is something you could do as well for a variety of use cases you could come up with. And this just creates more kernels in Jupyter. And once again, we're using Python code to do this, so we're not just dropping JSON files everywhere. We're trying to use the library to make sure that it's correct and it's more extensible for later. So You can see down below we're at the very, very last line, we're calling install kernel spec. That's a standard Jupyter API to install kernels. Anyone can import this library and use it for a variety of purposes. If you're not a kernel author, maybe this inspires you to try at some point to create a customized version of the Python kernel, or maybe a new language, or even more sophisticated containerization solution. It's really this simple, and I actually really didn't remove any code for this talk. What you see is more or less what runs. One other thing I just wanted to mention at the top is we use something called the Environment Kernel Spec Manager. So this is a customized version of the spec manager. It's also open source, but what this does is it automatically creates a kernel for every Conda environment or virtual env on your machine. So it just makes it easier if you're using one of those popular dependency management solutions to just automatically have those kernels created for you. We use this by default in SageMaker, but it's also pip installable or Conda installable. So now let's talk about creating those images. What happens? It's really a 6-step process. And remember, the goal here is to create a container that runs the kernel, but at runtime, it's running through the notebook in a headless way. So what do? First thing we do is we install a little helper library that we use for discovering those variables. I'll talk about that a little more later. It's called AST tokens. It's just a convenience library for reading through the Python code programmatically to discover variables. The second thing we do is we create a brand new Docker container. So I cheated a little bit. We actually don't use exactly the same container. We do create an interim container in the process. And this interim container is the one that's ultimately uploaded to Amazon ECR. Then we have a bunch of logic to copy everything that we can possibly discover, the environment variables that are currently set, the entire contents of the Python path, anything else that we can discover that is relevant to the current environment in Jupyter, that all gets copied into the interim container. Then the actual notebook file goes in there. So the notebook is in the container. Hopefully some of you get that reference. And then lastly, we create an entry point script. So when you run a Docker container, obviously there's no Jupyter server there. So we have to give it something to run at runtime when you call Docker run. So this is a special script that effectively orchestrates the running of the notebook in a headless fashion. Then we call Docker commit. We upload it to Amazon ECR. That's one API call, and the container is ready to be used. So one more deep dive. Let's talk about that entry point script that I mentioned. What happens when that thing gets run? Well, actually not a whole lot. The first thing that happens is we do that variable replacement. That's why that AST tokens library was installed as a final step. We go through the notebook file. We use the parameters that were passed in to the invocation of the Docker container, update the notebook so that the variables are all inlined, and now we're ready to run. How do we run it? We use nbconvert. Many of you have probably used nbconvert as part of your daily work. And if you've never used it, it's really just a simple application that executes a Python notebook in an environment of your choice, and it just outputs an HTML file or another notebook or a PDF, or there are a few other formats that it supports. So nbconvert runs. That might take a while depending on what happens. It could be seconds, it could be minutes, potentially hours if you're doing something especially sophisticated. And at the end of that, we write the HTML, and that we save it in Amazon S3, which is displayed by the various services that interact with this feature, like the IoT analytics feature. And if you've never interacted with AWS, we use another Python library for that as well. So all of this happens within Python code. We don't really shell out. It all uses SDKs and libraries available. And by the way, nbconvert we also import as a Python module. We don't even shell out to that. So there are a few things I felt that you might find interesting. Would be some of the decisions that we made while building this stuff, and understand some of the trade-offs we had to make. So one thing the team decided very early on that we would stick with most of the existing Jupyter front-end JavaScript stack. So we used Bootstrap, we used jQuery, we didn't introduce anything new. And the reason we did that is to make sure we had a very integrated, natural experience in Jupyter that wasn't loaded with branding or a different UX language. It feels very, very natural. It feels like it's part of Jupyter, and that's what the goal was. Likewise, this was so that as Jupyter changes, for example, moving over to Jupyter Lab, we could apply the same philosophy, build a natural experience in that environment so that we don't have this mix of unfamiliar or just jarring experiences. And one lesson that we learned while building that front end was while we were building that wizard. So on the browser side, how do you figure out what's happening on the server side, particularly within the kernel? That's a little challenging. So a little trick that we did, and you can review this in the source code later, is we actually create a temporary cell in memory. We send it off to the kernel, and we use a little magic called whols. So if you open up a Jupyter Notebook now, you run that whols magic, it'll actually give you a nice parsable listing of all of the variables that are currently in the process. So you can try that out. It's a neat little thing. And the idea of creating a temporary cell that's not visible, sending it off to the kernel, is a nice way for the browser to kind of get a sneak peek so that we can display that nice wizard with all the variables. On the back end, just one decision I felt you might find interesting is that we moved all of the Amazon ECR calls to that Python code. So AWS has a variety of SDKs. There's one for Go, there's one for JavaScript, there's one for Python, obviously, there's a C++, there's a C#. Pretty much all the languages have some form of an AWS SDK. So we could have done a lot of this from the JavaScript side, but that meant moving credentials to the JavaScript side. So by doing everything on the server, we prevent dealing with all that mess. So pretty strong line, anything that happens to call a remote service happens from the Python code. And then just a little lesson that we learned is try not to block Jupyter. If you do too much all at once, you can make Jupyter unresponsive. So use that Python async keyword. That's a really, really good way of making sure you don't break Jupyter by having it freeze if you're doing something that takes a long time. Okay, so that just about wraps things up for these two implementations. Taking a look back at the questions I posed at the beginning, here's what I hope you can walk away with. One, I hope I've expanded your ideas on what you can really do with containerization, specifically of kernels and individual notebooks. I tend to feel that there's a large number of possibilities and potentially could be applied to a variety of different use cases. And it's actually, at the end of the day, not an especially complicated matter. And it's something that's very approachable to anyone familiar with essentially just surface level understanding of how Jupyter works. Two, I hope you could see two different use cases, one of which is more quickly iterating on an algorithm. The second is actually taking the notebook so that it's a reproducibly run bit of code, so kind of turning that notebook into a production application. There are a lot of examples at JupyterCon this week, as well as last year, where this is an active area of investigation and research with anyone using Jupyter. Three, we've done a couple of deep dives. I hope you found those interesting. Armed with just a little bit of knowledge on how Jupyter works and how it surfaces at kernels, and getting some of those Docker networking magics correct, it's actually pretty straightforward to do this on your own. And the fourth thing, how do I get started? I'll give you a couple of things. The first thing, of course, is using that IoT feature. I hope you try that out. Oleg will be very happy if you do. But it's a really, really fantastic feature for IoT customers. And it really is that easy. I'm not really glossing over anything about how it works. And the second thing you could do is download our code. The Jupyter plugin that we wrote is completely open source. It's on GitHub. I'll have the link on the next slide. And download it, play with it, fork it, contribute changes to it. Make it work, for your use case. And just as a reminder, there isn't actually anything very IoT specific. If you're not doing Internet of Things related work, if you're just working through tables of financial data, this works just as well for that use case. And you might even be able to get this thing running locally. There's actually nothing SageMaker specific in this code. It's totally applicable to a variety of use cases. So that pretty much wraps things up. These are a couple of the links. I will upload all of these slides to the JupyterCon website. So they also include a more or less accurate transcription of this talk in case you missed a detail or two. And yeah, thank you so much.